In this lecture, let us discuss some example of discrete random variables which are used extensively in practice. So first one is called Bernoulli random variable or Bernoulli distribution. So what is the scenario? The scenario as follows that suppose we have a random experiment which has two outcomes, and these outcomes are generally denoted by success and failure, but not that this success and failure just two words to denote these two uh, outcomes. It could be any outcomes. For example, suppose I am tossing a coin, I can have head or tail, so two outcomes. Maybe I call a getting a tail as a success and getting a head as a failure. I can We can talk about if a person is infected by coronavirus or not. Then also we have two outcomes: the person is infected or the person is not infected. We may say that, well, if the person is infected, then this is a success, at least success from the virus point of view. If it is not, if it is not infected, if the person is not infected, we have a failure. We can talk about uh, if a mobile phone works more than 3 years or not, and also we have two outcomes that the mobile phone works more than 3 years or mobile phone do not work more than 2 years. So all these scenarios we have this kind of experiment where I have two possible outcomes, and it is customary to denote these two possible outcomes as a success and as a failure. Okay, so this success failure setup is very useful, many practical scenarios, and the idea is that whenever we have exactly two outcomes, or the outcomes is categorized into two types, then we can actually talk about some Bernoulli distribution. Okay, so the scenario is like that. I have a sample space which consists of 2 points, success and failure. Now we define a random variable x, which is 1 if s occurs, that is success occurs. On the other hand, x is 0 if failure occurs, that means f occurs. Okay, so clearly this x is a function from this sample space to R. That means this x is a random variable. And in this case, if I know what is the probability of S and what is the probability of failure, what is the probability of success and what is the probability of failure, I'll able to find out what is the probability that x equals to 1, because probability x equals to 1 is exactly same as probability of occurring success, and maybe we denote it here by p. Okay, we denote it here by p. The probability of success is denoted by p, and similarly the probability of failure will be 1 minus p. So clearly probability that x equals to 0 will be 1 minus p. So in this case, the distribution function can be written in this form. If it is x is negative, the probability that capital X less than equals to small x will be 0, because capital X cannot take any negative values. If small x lies between 0 to 1, 0 inclusive, 1 exclusive, then the probability is 1 minus p, because in this case, only possibility that a failure occurs. When x is greater than equals to 1, both the possibilities come, x equals to 1 and x equals to 0, so that probability, the sum of the probability turns out to be 1. Okay, so this is the distribution function corresponding to the random variable x. Now it is easy to see that this distribution function is a jump, is a step function, and if you add up the length of the jump, it turns out to be 1. So in this case, clearly, if I take the set 0 and 1, if I take the set 0 and 1, so in this case, it is clear that in this case, it is very, very clear that if I take the set, so this is example, which example? Example number 2.10. So Bernoulli random variable or Bernoulli distribution. So in this case, if I take that the set D is 0 and 1, in this case easy to see that probability x equals to 0, which is already we have discussed, it is 1 minus p is same as 1 minus probability x equals to 1. And in this case basically both the probabilities are greater than 0. If p not equals to 0 and p not equals to 1, then both the probabilities are greater than 0, and and sum of the probability x belongs to d, which is 1. So that means taking d as a support, this a random variable x is a discrete random variable. Okay, so that means that, well, this case I have a discrete random variable, and this discrete random variable, and it is again very easy to see that the PMF is 1 minus p if x equals to 0, p if x equals to 1, and 0 otherwise. There is a typo, that there will be 0 otherwise case will be here, so there is a typo, please correct it, that we have 0 otherwise case here. And if a discrete random variable have this PDF, then that discrete random variable is called Bernoulli random variable with parameter p. Note that if I change p, that is the PMF will change. That means the probability of success, probability of failure changes, distribution function changes, the probability mass function changes. Okay, so this p is called the parameter in this case, and we use the notation that x follows this tilde notation. This tilde means follows, x follows Bernoulli p, and that basically means that if I write x follows Bernoulli p, that basically means that x is a discrete random variable and has this PMF, or equivalently you can tell that this cumulative distribution function p CDF. Okay, because CDF and PMF has one-to-one correspondence, so they are equivalent to say that x has this CDF, or x has this PMF. Okay, clear? I hope this example is clear, and the basic idea is that, well, the outcome is basically either success or failure kind of thing, and x is taken to be 1 if I have a success and 0 if I have a failure. Note that this 1 and 0 is again some number. Actually I can take it is 1 and 2, I can take it is 5 and 10, I can take 1000 if a success occurs, and 1001 if a failure occurs. So it is just completely up to us that what value I will assume, but the thing will remain same. Only thing is that, well, the distribution function will change in the sense that the jump will be in different place. Okay, if I suppose if I take x equals to 1000 and x equals to 1001, if x equals to 1000 if a success occurs, x equals to 1001 if a failure occurs, then basically this function turns out to be 0 if x is less than 1000, 1 minus p, p if 1000 is less than equals to x is less than 1001, and 1 if x is greater than equals to 1001. So the jump changes, maybe p1 minus p also change, this p and 1 minus p also change depending on whether I am giving smaller value if a success occurs, or give bigger value if success occurs. Based on that may change, but thing will be almost same. Okay, so I hope the Bernoulli distribution and when we should use the Bernoulli distribution is clear to you. Next one is binomial distribution, and this binomial distribution you can think of a generalization of the Bernoulli distribution. In what sense is a generalization? So in case of the Bernoulli distribution, I do the random experiment just once and I have the outcome, and I classify it into a success or into a failure. Now in the binomial distribution, I will repeat the experiment n number of times. Okay, I repeat the experiment n number of times. Obviously we need independence to write down different kind of probabilities, so we also assume that we repeat the experiment n times independently. Just for example, to see that in the Bernoulli case, if I toss a coin, it is a Bernoulli experiment in the sense that I have two outcomes, either head or tail, and I take maybe the random variable takes value 1. If a head occurs, it takes value 0 if a failure occurs. Now in the Bernoulli distribution, what I am doing, I I am repeating the toss and I am noting down what are the outcomes. So I have basically the sample space turns out to be basically when I toss the n times, so n outcomes will be there, omega 1 to omega n, and each of the outcome belongs to the success set success or failure. In our example, in the point testing example, it is head up tail. Okay. Now, if I denote a random variable x, if I take a random variable x, which is nothing but number of successes, which is nothing but number of successes out of n Bernoulli trial, then we can see that this random variable x is a discrete random variable, intuitively very clear, because this x will going to take 0, 1, 2, 3, 4 up to the value n. Okay, so it is very intuitively very clear, it will going to take the discrete values, so it will be a discrete random variable, mathematically proof also we are going to do. So in this case, as we have already made, I have already pointed out that if we take x can take the values only in the set 0, 1 up to n. So I will start with this set. Note that this is a finite set, so this is a at most countable set. Now, if I try to find out what is the probability that x equals to k for different values of k in this set. So let us start with the simple one, that probability x equals to 0. Okay, so we are talking about binomial distribution, so we are talking about example 2.11, example 2.11, the binomial distribution. So in this case, I have the set D is 0, 1, 2 up to n, and we are trying to find out what is the probability that x take value 2, what is this probability for different x belongs to the set D. Okay, now note that in this case, if I try to find out what is the probability x equals to 0, it is very easy to find, because x equals to 0 means no success occurs. So all the n trials give us a failure. And so this probability is 1 minus p whole to the power n, because 1 minus p is the probability of failure. On the other hand, if I try to find out what is probability x equals to n, this is also very simple. This basically means that all the outcomes are successes. So that means it is nothing but p to the power n. Note that to writing p, this probability x equals to 0 equals to 1 minus p to the power n, or to write probability x equals to n is p to the power n, we are actually using the experiment, the trial of the experiment are independent. If they are not independent, then I cannot write the probability of all of them are failure is equals to product of the probabilities that each of them are failures, which is turns out to be 1 minus p to the power n in this case. Now let's talk about some general value, probability x equals to k, where k belongs to the set D but not equals to 0 and n. So two extreme points I am just removing, the middle point I am trying to find out. Okay, so when we have x equals to k, we will have x equals to k if we have exactly k successes and n minus k failures. So exactly k successes means I have p to the power k, and the probability of having exactly n minus k failures is 1 minus p to the power n minus k. Now note that this is going to give me the probability of one of the arrangements. So what do I mean by one of the arrangements? So suppose, for example, I take n equals to maybe 3, and I try to find out what is probability x equals to 1. So if I have some particular arrangement like S, F, F, then this probability of this one is basically nothing but p to the power 1 into 1 minus p to the power n minus 1, which is 3 minus 1, which is 2 in this case. Now note that x equals to 1 can occur for all of these arrangement, all of these three arrangements. All of these three arrangements, success, failure, 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 success, failure, 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 success, for all of these three arrangements, the x will take value 1. So when I try to write this probability in this case, it turns out to be obviously this probability are same for all this arrangement. The probability are same. This probability is p to the power p into 1 minus p square, p into 1 minus p square. So in this case, I have to basically multiply it by 3, which is basically 3c1. So how many arrangements are there having exactly one success and two failure? That number is 3c1. So I have to multiply this probability by 3c1. Similarly, in this case, I have to multiply this probability by ncx, and that will be sorry nck, and that will be the probability for all k belongs to the set D. Clear? This discussion I hope is clear that actually these two things is coming. This part is coming because this is the probability of one particular arrangement, and this part is coming because there are nck possible arrangement of success and failure such that x equals to k happens. Okay, fine. I hope this example is okay. So now, so what I get? We get that probability x equals to k turns out to be nck p to the power k 1 minus p whole to the power n minus k if k belongs to D. Now, if I take the sum of this probability over k belongs to D, that is sum of the probability over k belongs to D, which is basically nothing but sum of this quantity, sum of this. So this is sum of this, and this turns out to be 1 because this is nothing but the binomial sum. This turns out to be p plus 1 minus p whole to the power n. So that basically makes that sum is 1. And so what does this mean? This means I have a finite set which is at most countable set such that probability of x equals to x, capital X equal to small x, is strictly greater than 0 for all x belongs to D. And when I try to find out probability that x belongs to D, which is nothing but sum of these probabilities, that turns out to be 1. So x is a discrete random variable, and in this case PMF we have already found out it is nothing but this quantity if x takes values 0, 1, 2 up to n, and the PMF is 0 if x does not take the values 0, 1, 2 up to n. So that means that if I count the number of successes, that is a discrete random variable, and in this case we will have this is the PMF of that discrete random variable. And we say that the distribution of a discrete random variable having this PMF is called a binomial distribution. Now note that in the previous case, in case of the Bernoulli, we have one parameter p. If I change p, this probability changes, so the PMF changes. But in this case, I have two parameters. One is p, another is n. So if I change p or n or both of them, the probability will change. So now this is called a binomial distribution with parameters n and p, and the corresponding random variable is called the binomial random variable. And we will use this notation that x follows binomial n comma p to denote that x is a discrete random variable having this PMF. Okay, fine. I hope the binomial distribution is clear. Now note that I have already pointed out the fact that in case of the Bernoulli random variable, this 1 and 0 I can change based on my choice. But there is one plus point taking 1 and 0. The plus point is that, see, in case of the binomial random variable, I have multiple trials. So for each trial, I can define a random variable xi which takes value 1 and 0 it takes value 1 if I have a success and takes value 0 if I have a failure. Okay, so the scenario is something like this. So I have n trials. So now I define xi is equals to 1 if success occurs and 0 if failure occurs. Note that this xi is for all i's 1, 2 up to n. So that means that I have x1 which tells that whether the first one is a success or failure. I have x2 it tells that whether the second trial is a success or failure, and so on. I have xn. Xn tells that whether the last trial is success or failure. Now, note that if I add them up, it is basically nothing but our x, which is the total number of successes in n trials. Okay, so that basically says that, well, if I take the Bernoulli random variable as 1 and 0, that has a benefit that if I take the sum of those Bernoulli random variables, it basically tells us how many successes are there. And similarly, if I just change this definition little bit by taking yi is equals to 1 if failure occurs and 0 if success occurs, then it is clear that if I take the sum over I of yi, it is nothing but total number of failures. Okay, so there is a benefit defining the Bernoulli random variable is 0 and 1. But yeah, other things also comes into the picture. We will see another example, another particular assignment when we go for the stochastic processes, that is basically Markov chain. Okay, so let us discuss the next example, next distribution, which is called the geometric distribution. So geometric distribution again coming from the Bernoulli experiment. So in this case, in the case of the binomial distribution, what we do, we basically do some finite number of trials, Bernoulli trials. But in this case, I will do a continuous trials. So I'll keep on tossing a coin. And if I do this one, then I have a infinite sequence of W1, W2, and so on and so forth, where each Wi belongs to each Wi either a success or a failure. Okay, and note that in this case, this S also going to have infinite number of coins. So it's just like this. If I toss a coin infinite number of times, I have some sequence of head, tail, and that go up to infinity, and that have a countable number of times. Okay. Now you see that, well, this is not a countable because this is a binary sequence, collection of all binary sequences. So it is basically an uncountable set. So S is here basically an uncountable set. Now what I am doing is that I will stop. Instead of doing it infinite number of times, suppose think of this scenario that I will stop whenever first success occurs. So if I toss a coin, I will stop when the first head occurs. So that means the sequence is head, the sample space is head, tail head, tail head, tail head, and so on and so forth. Now this sample space is turns out to be a countable one. And X denotes the number of failures before the first success. So what does this mean? This basically means that, well, if example 2.12, right, or 13, 2.13. Example 2.13 is basically, well, so I have head, and if I talk about X of head, that is basically 0. So there is no failure before the success. If I call a head as a success, okay. Then if I have tail head, it basically gives me 1 because tail is a failure and there is exactly one failure before the first success. Then if I try to find out head, tail, head, that turns out to be 2 and so on and so forth. Okay. So basically, if I take x to be the number of failures before the first success, then basically x can take value in the set d, which is 0, 1, dot, dot, dot. So now this, see, in the last two examples, the case of the Bernoulli as well as the binomial, the support was a finite set. In case of the binomial, it is 1, 2, 0, 1, 2 up to n. In case of the Bernoulli, it is 0 or 1. Now, in this case, it will be a countable set, but not a finite set. 0, 1, 2, and so on and so forth. And note that in this case, I can find out the probability that x equals to k very easily, because what does x equals to k mean? X equals to k mean that there are consecutively k failures, then a success. So this P comes from the success. Last trial is a success. From that one, this P comes, and the first k trials result in a failure. So I have 1 minus P whole to the power k. So the probability x equals to k is nothing but P into 1 minus P whole to the power k. Now notice that if I try to find out what is the probability that x belongs to D, which is nothing but sum of probability x equals to k for k belongs to D, and that sum turns out to be D, and this is a simple geometric sum, so that's why this quantity equals to 1. So that means that random variable x is a discrete random variable which support D, and probability mass function as 2.4. Probability mass function is 2.4. And if x is a discrete random variable having PMF this, then we call that the distribution of x as the geometric distribution with parameter p, and the random variable as the geometric random variable, and we use the notation x follows GEOP. Okay, clear? I hope the these three things, Bernoulli, binomial, and geometric, is clear with everyone. And you see that we start with the Bernoulli and then generalize to binomial, and we then basically see a little bit variant of that, which is geometric. Okay, I leave one exercise for you. See, note that in this case, x is taken to be first number of failure before first success. If I change this first, suppose I take x is the number of failure before the rth success for some given value of r. Okay, try to show that this x, the new x, is also a discrete random variable, and try to find out its PMF. Next example we are going to see is Poisson distribution. So for the Poisson distribution, I am not going to give you the exact background like I have given for binomial, Bernoulli, and geometric, but we start with this function. Note that if I take this function, it is easy to show this function is a PMF by taking this is D, and so on this D, on this set D, it is basically strictly greater than 0, and this D is a countable set, and if you take the sum, it turns out to be 1. So clearly this f function is a PMF, and if a random variable has this PMF, we say that the corresponding random variable is a Poisson random variable, and the corresponding distribution as a Poisson distribution. Note that in this case I have one parameter lambda. If I change the lambda, the PMF changes. So lambda is the parameter, and lambda has to be greater than 0. Otherwise, this may not be a probability mass function. Okay. So as I pointed out, okay, we will use this notation x follows POI lambda to denote that x is a discrete random variable having this PMF. As I pointed out, as I already mentioned, that I have not given you the exact background of Poisson random variable, but we will discuss this one later when we have more tools of probability. And what we are going to show is that the Poisson distribution is a limiting case of the binomial distribution when the number of trials is very, very large. When the n is very, very large and p is quite small, then the binomial distribution can be approximated by the Poisson distribution. Okay, whatever I told it quite vaguely. We are going to see these things precisely as we progress. But just for information, that as this is the approximation of the binomial distribution for large n and small p, that means whenever I can use the binomial distribution, I can also use the Poisson distribution provided the n is quite large. Some examples that uh, if I try to model the number of accidents in a particular spot of a city, I can use the Poisson distribution because number of accidents is basically you can take as a large number of cars are moving and out of them how many cars are making accidents. So that means basically how many cars are making accident, and that means basically n is quite large because there are a lot of cars, and I am counting how many of them making, how many of them having some accident. So that is basically accident in this case is basically success. So it is a binomial kind of a thing, and if n the number of cars is very large, I can use a Poisson distribution. Similarly, the number of misprint in each page of a book, because there are large number of words in particular page of a book. So again, I am counting number of mistakes. So that is basically success is basically mistake, and so this is a binomial scenario. And as the number of words is very large, so n is very large. So I can use a Poisson distribution in this case. Okay, so on and so forth. So Poisson we can use whenever we have a binomial scenario, but n is quite large and p is quite small. We can use Poisson distribution. Let us see a very simple example. What this example says that well, I am trying to compare two kind of aeroplane. One has two engines, another has four engines. So what we know is that the probability that a engine fails during a flight is 1 minus p, and engine works independently. So suppose that an airplane engine will fail when in flight with probability 1 minus p independently from engine to engine. So if I have a multiple engine, failure of one engine will not change the probability of failure of the other engine, which is little bit hypothetical. In practice, it may not be true, but for the time being, let us assume this. The aeroplane will make a successful flight if at least 50% of the engines remain operating. So that means that if I have a two-engine aeroplane, then if at least one of them works, then the aeroplane will fly without any problem. Okay, as each engine is assumed to fail or function independently of what happens with each other engine, it follows that the number of engine operating is a binomial random variable with parameter p. So if I call that x is the number of failure, no, sorry, number of success, that means number of working engine, then x is a binomial random variable. What is n? N is how many engines that particular aeroplane has, and what is the probability of success? Probability of success is that a engine do not fail. That means it is working properly. That probability is 1 minus p, which is p. Okay. So now what we have? We have that we have that we have suppose two random variable. One is x, which is number of working engine in a two engine flight, and y is again the number of working engine in a four engine flight. Okay, so clearly in this case x has a binomial distribution. What are the parameters? Parameters are 2 and p, whereas y has a binomial distribution with parameter 4 and p. Now, if I try to find out the success probability for a two engine plane is nothing but x is at least 50% has to work, and because I have two engines, so means at least 50% means that either one engine work or both the engine work. Okay, so the success probability for a two engine plane is nothing but probability x is greater than equals to 1. On the other hand, the success probability of a two engine plane, a four engine plane is nothing but probability that y is greater than equals to 2 because in this case at least two engine has to work. Okay. Now let us make a comparison of these two. That so that means that success probability of a two engine plane is nothing but this quantity. It is written from the binomial one, that nc2 p to the power 2 1 minus p to the power n minus 2, and in this case n equals to 4. That's why we get this one. And I try to find out what is the probability that y is greater than equals to 2, so that sum up that these 3 points. And it, if you simplify it, it simply becomes this way. Similarly, for the two engine plane, the success probability is nothing but sum of these two probabilities, which is basically this corresponding to x equals to 1 and this corresponding to x equals to 2. This is the probability x equals to 2, and this sum of 2. Now, a four engine plane is if safer if this success probability is more than this success probability, and which tells us that if p is greater than equals to 2 by 3. So what does this mean? This means if the success probability of each engine is more than 2 by 3, then a four engine plane is safer, otherwise a two engine plane is safer. So that means that if the success probability is small, then having small number of engine is better, in the sense that if I have a large number of planes, large number of engines, then as the success probability is small, there is a possibility that large number of failures. Okay, so that's why basically in this case we got that if p is greater than 2 by 3, greater than equals to 2 by 3, a four engine plane is safer than the two engine plane. If small p is less than 2 by 3, then a two engine plane is safer than a four engine plane. Okay, I stop here.